We are Team Future Engineers of America, and for our 152 design project, we decided to look at the analysis of a skateboard and how making changes to design can make a more reliable and safe product. For our initial design, we conducted a static study for someone not moving on the skateboard. We simulated the weight of an average rider to be about 62 kilograms, which translates to a 620 Newton distributed load or 0.006 megapascal pressure load. There are 8 fixed boundary conditions applied at the drill points on the deck. The study resulted in a max stress of 10 megapascals and a maximum displacement of 0.4 millimeters. Another static study was conducted for when the rider is doing a trick on the board. Now there are only 4 fixed hinges at the front drill points, and there is an additional load applied to the back clip. The maximum stress result is 2.7 megapascals and a maximum displacement result of 7 millimeters. A closed form comparison was conducted to compare the FEA solutions and our own calculations for the skateboard during aerial tricks. The solution was formed by equating the board to a beam with a fixed restraint and a roller restraint on opposing sides. The closed form solution provided close predictions but were not as accurate as the FEA solutions. The errors for the closed form comparison was 50% and 22.86% for the stress and displacement errors respectively. Impact loading was simulated by calculating the force exerted by a 0.5 meter drop with a deflection of 0.4 millimeters. This resulted in an additional impact load of 10,700 newtons, but the maximum stress reached 289 megapascals at the fixtures, with a maximum displacement of 7.41 millimeters in the middle of the board. The deck is still far from yielding. A modal analysis of the wheels was conducted by applying a roller support boundary condition on the inner wheel face and then applying a 155 Newton load vertically downward. The resonant frequencies for the first 5 modes are included, and the modal analysis indicates that the wheels are most susceptible on the outside. This matches real-world applications where the wheels are interacting with the ground due to friction. A static study was conducted on the trucks by applying roller supports on the axles and a downward pressure load of 0.003 megapascals, which is the load that each set of trucks will experience. A maximum stress reached 0.2 megapascals and a maximum displacement was reached of 0.00017 millimeters. Furthermore, a fatigue test was done, resulting in a fatigue lifespan of 35 million cycles under our impact load. Due to the long lifespan, it was concluded that the system will not fail due to fatigue under normal circumstances. Our first design iteration was changing the flat deck to a concave up deck and reducing the thickness of the board from 0.4 inches to 0.3 inches. This was done to redistribute the stress and to remove stress singularities that were building up near the fixed supports. The design changes resulted in reduced maximum stress and maximum displacement. The initial design had huge stress points all along the interface of the drill points. Our design change reduced this and isolated points of high stress to just portions of the interface. For our second design iteration, we simplified the geometry and changed the materials of the trucks. As a result, there was a decrease in overall displacement for the trucks under load, and it minimized the points of maximum stress. However, the maximum stress for some points on the assembly were not reduced. In conclusion, during our project, we ran studies on the initial design to locate stress concentrations, compute closed-form solutions, and conduct impact loading analysis to simulate real stresses from aerial moves. Our design changes had real-world applications, such as durability and reliability, in mind while reducing overall stress by 24% and 58% for basic static and impact loading studies respectively. Thank you for watching our presentation.